hello, everyone. We really appreciate you being here, and we hope you will get valuable information about understanding names with neural networks during this webinar. My name is Jeanne. I run Basis Technologies International Operations from Singapore, and I'll be your moderator today. I'm going to make sure all your questions are answered, but I'm sure you've noticed that you've been muted. So to submit a question, you need to click on the Q&A icon that you can find on the bottom of your screen. You can ask your questions throughout the presentation, but they will be answered and addressed at the end. Just a little heads up, at the end of the webinar, you will be directed to a survey. I would love it if you could just take 1 minute to let us know your opinion. These feedbacks are very, very important to us. This webinar is being recorded, and we'll be emailing out the link tomorrow to everyone who has registered. So if you find it useful and informative, please feel free to share the link with anyone who might be interested. While we wait for other people to connect, I'll just take 2 minutes to explain to you what is Basis Technology and let you know a little bit more about Rosette, our text analytics brand. Basis Technology has been around for 25 years. And since the beginning, our mission has been focusing on getting structure and meaning from unstructured text. Think reports, articles, social media posts, comments. We pride ourselves with providing a high quality, carefully curated and tested set of text analytics and natural language processing capabilities. We also pride ourselves, as you can see, with comprehensive natural language processing coverage. This includes both breadth of capabilities, from providing the building blocks of text analytics, which are language identification and morphological analysis, to delivering the more advanced tools like cross-script semantic search and, of course, cross-script fuzzy name matching. Rosette enables high-quality analytics in over 32 languages, including non-Latin scripts: Korean, Chinese, Arabic, Japanese. One thing to note is that all the Rosette capabilities are highly adaptable, with easy tools for domain adaptation, and it has many options for deployment. We work with our clients to engineer the best possible natural language processing solution for their needs, using every possible data source to make their AI smart and resilient. Now that I think about it, major brands that you know deploy Rosette on-premise and in the cloud for their mission-critical and high-volume systems. But the reason we're here today is because we have also put a lot of effort and R&D in developing a highly sophisticated fuzzy name matching algorithm that doesn't rely just on rules, but includes machine learning and deep learning models too. This tool is capable of catching many name variations and phenomena. At first, this technology was developed for governments, and it's been used in many immigration and counterterrorism applications, but it is also now being used in anti-money laundering, onboarding, know your customer systems used by financial institutions around the world. In fact, today we will be interested in showing you the more technical algorithmic side of the product and share with you some of the research projects we have been working on recently. And it's going to be less about how to technically operate the product. And that's all I'm going to say about Rosette and Basis Technology. So let's kick this off. We're going to be together for about an hour, 40-minute, well now 35-minute presentation, followed by a 15-minute, 20-minute Q&A session. So let me introduce you your hosts for today's talk. With us, we have Kfir Bar. He's the chief scientist of our text analytics team and head of R&D. He has spent many years working in a wide range of natural language processing disciplines. And fun fact, he plays keyboard in not one, but 2 rock bands. With him, Philippe Blair, who is a senior research engineer, and he's been with Basis for about 4 years now. He is the critical link between our R&D team and our product team. And when he's not working, he is an avid traveler whose goal is to eat something in every country around the world. Finally, today we have Carmel Eliav, who has been with Basis for 2 years as a research engineer. She's been focusing on writing the neuron of our name matching algorithm. She's also served as an Army intelligence officer for 8 years. Well, I'm sure you don't want to hear from me about fuzzy name matching and deep learning, so I leave it to these three great minds to tell you all about it and let you know why names are so hard to deal with.
Thank you, Jen. Thanks for the introduction, and hello, everybody. Let's kick this off. So processing names is important for many applications, including financial compliance when banks, for example, need to match records based on person or company names, or even search a large international list of high-risk people, what we would typically call a watch list. The problem is that there are many names out there, right? There are different variations, nicknames, and not to mention the different ways for how to transliterate them in different languages. The name search is also important for border control when someone arrives with a foreign passport, for example, and a name written in both Latin script and the original language, and then searching this name in watch lists or matching that name against existing records in a large knowledge base requires a more comprehensive technology than just simple text lookup procedures. So the task is called name matching, and it starts with a pair of names for which an algorithm needs to calculate a matching score. And that score reflects how similar those names are. So for example, here you can see President Roosevelt or different variations of President Roosevelt's name. So the first one on the left is written in Latin script, and it's a full name variation, whereas the other two are written in completely different scripts and languages, and we still want to match them against their original name. So when matching two names, one would face many challenges. There are phonetic challenges, there are spelling differences, missing components, nicknames, and of course, there's the challenge of matching the same name when written in different scripts and or languages. And that's what we're going to talk about today. In addition to matching pairs of names, we have plugins for search engines, search platforms such as Elasticsearch and Solr. It's called Rosette Name Indexer, or RNI, which enables name search by addressing all those challenges I mentioned before, using some machine learning algorithms, which we'll mention today. About RNI, given a name to be found in a watch list stored in one of those search engines, Solr or Elasticsearch, RNI runs in two passes. The first pass, it generates a relatively large set of candidates. And then in the second pass, it uses different types of algorithms to produce matching scores for all those candidates so that it can filter out those candidates that, that their score is below a certain threshold. Our name matching algorithm in general supports different types of entities, as you can see here. We have person names, organizations, locations, dates, addresses, and we support currently about 18 different languages. Now, specifically about the algorithms, we use various types of algorithms in order to produce that matching score I mentioned before for a given pair of names. So for example, for simple misspellings, we use edidistance calculations like Levenshtein distance. For misplacing name components and to support the variability naming convention, we use different rules. Then we have phonetic models, and we're going to focus on these models today. Those are for matching names that have similar sound, including names that are written in different scripts and languages. We have semantic algorithms based on embeddings, mostly word embeddings used to match name parts that have similar meanings, like university and college if you want, or LTD and Inc. for company names, and so on. Also, I would like to mention that our users have full control over the configuration of those algorithms and the way that we aggregate their scores into a single score by assigning weights for those individual algorithms based on their need. So in what follows, my colleagues Philip and Carmel will from our research team, and they will talk about our journey in building data-driven neural network for phonetic name matching. For now, in this session, we will be focusing on name pairs in which one name is written in Japanese, katakana, and the other name is written in Latin script. Philip will begin with explaining a relatively simple data-driven approach based on a hidden Markov model, and then we'll continue to explain more about our recurrent neural network, RNN, that we're using, and then finally we'll talk about a convolutional neural network solution in order to balance between accuracy and matching speed performance. And I'll just mention that this session will be technical, and it's like Jen said before, it's focusing more the algorithmic part of the product and our experiments that we are doing, and it's less about how to operate the product in terms of its functionalities. But I promise to you that it's going to be very interesting. So Philip, take it away.
Great, thanks. So yeah, as Kafir said, I'm going to be starting out by giving an overview of a more traditional approach to data-driven name matching using hidden Markov models, or HMMs for short. So we're not going to get into all of the mathematical technicalities of how these work, but the goal here is to give you some kind of intuition to understand what problems we're trying to solve with our deep neural network approaches. So when developing an HMM, the first step that you need to do is have some sort of ability to describe names in one language statistically. And the way that we do that is we take a large data set of names and we just look at the probability of one character coming after another. And we build up a big diagram like this, which is just a big state machine. And each of these arrows in the state machine represent the probability of transitioning from one character to another. So then, in a statistical sense, a name is nothing but a walk through this graph. So we're going to focus in on John here. And once we have the ability to describe this sequence, we want to know how can we actually use it to do name matching. So the solution's rather straightforward at a high level. What we're going to do is, in addition to modeling the dynamics of a single language, we're going to model the probability of words in our target language corresponding to English words, or English characters. So for example, here you can see that we have the proper transliteration for John bolded. And we would expect this to be kind of the highest probability set of Japanese characters corresponding to these states. And so once we can do this, the actual scoring process is rather straightforward because we just combine these two probabilities into a single score. We just take the probability of seeing this given John sequence, the probability of that corresponding to the Japanese words that we're seeing, and that's it. So that sounds rather easy, right? Problem solved, except if anyone here can speak some Japanese, you might notice there's something a little awkward about this diagram. So if you remember from what I said before, we learned to model the dynamics of English on their own, and we learned to model the correspondence between English to Japanese on its own. And so this letter O state is meant to represent the letter O in all possible contexts in English. However, the choice of transliteration we've chosen for O really only makes sense in the context of following a J, which is a bit strange, right? I mean, O, in theory, we should be favoring this first entry of this table. And this is really just a single instance of a broader problem when doing cross-lingual name matching. The correspondence between characters in our source language and our target language is not always, in fact, is almost never one-to-one. So, this specific issue can be addressed by adding some fancy states to our HMM, which kind of model this diphthong style phenomenon. But even doing that requires some amount of domain expertise because you need to know which extra states you should be adding. Even worse though, there are specific morphological effects that you really can't even compensate for that way. For example, there's a phenomenon in Arabic where the suffix of a word the suffix of a name can affect the earlier part's pronunciation, which perhaps would affect the transliteration. So I think a good way to illustrate this to an English-speaking audience would be if you add the letter Y to the end of the word photograph, it becomes photography. And so that middle syllable changes based on the presence of that last letter. So as such, we really would like some more general way of modeling context when doing name matching. And the unfortunate fact is that solutions for doing this with HMMs either don't scale to long sequences of characters, or they're just too computationally intractable to be usable. So how about we just try something different, right? Let's think about how you would transliterate a name as a person. So here's one option, which is really what the HMM is doing, if you think about it. You look at your input name, you read a small chunk of it, turn around, write the transliteration for that, turn back around, read the next chunk of the name, write the next transliteration, and so on. Although arguably this is even a little more flexible than the HMM because you have some ability to discern what these chunks are, but I digress. The fact of the matter is this isn't really a natural way to do transliteration though, right? Especially if you're well acquainted with both languages. But really just to hammer this point home, let's take a closer look at why exactly this approach is not suitable for doing transliteration. So at a high level, abstractly, if we think about what the HMM is doing from a machine learning perspective, we're essentially taking every input character and we're associating 0 or 1 output characters. And so this effectively is a form of what's known as sequence tagging or sequence labeling, which means that we're kind of forcing this correspondence between the shape of the input and the shape of the output. And it's a bit too rigid, right? I mean, we would like to be able to have some natural way of grouping together parts of the input or grouping together parts of the output in order to model these many-to-one or one-to-many style of relationships between characters in different languages. And there's just not a natural way to do this with this sort of formulation. So here's an alternative. So again, if we assume that you're well acquainted with both languages, names generally wouldn't be too complex to just remember, turn around, and write down the transliteration. And so in effect, what you're doing when you do this is you're compressing the name into some portable notion of that name, which you can then use to produce this transliteration from that notion alone, without necessarily having to refer back to the original name. So at a high level, this is what we would like to do, but how can we actually accomplish it? So the good news is we need look no further than work that's been done in neural machine translation. So this is a similar problem, except instead of transliterating a single name, they're looking at translating an entire sentence or document or so on. So you can imagine that this phenomenon is especially pronounced in this domain, right? I mean, in different languages, you have different word order, different grammar, and so on. And so you really need some way of representing the input that's extremely flexible. And so what scientists came up with was this notion of a sequence-to-sequence architecture, or seek-to-seek for short. And this process is essentially what we just described, where you have an encoder module read in the input one word at a time, and then it condenses it into some portable vector, which is a kind of a notion of that input. which then gets fed to a decoder module that produces the translation of the input one word at a time. So because of all of the earlier described issues with HMMs for name matching, we felt that this would be kind of a natural problem setup for what we're trying to accomplish. So just to dive a little more technically, a natural question might be, what do these encoders and decoders actually look like? So typically they are a form of recurrent neural network, or RNN, and these come in a few different flavors. But the upshot is that they're just a piece of a neural network that is designed to process sequences of input. So, if you have a sequence of text or characters or whatever, you simply just pass in each one at a time, and it will simultaneously build up some understanding of that sequence while also producing some sort of output representing that specific item in the sequence. Now, for our purposes, we chose a flavor of RNN known as a long short-term memory cell, or an LSTM. This is a fairly popular choice for at this point slightly older approaches to neural machine translation. Again, I'm not going to dive into all of the technical details of what this looks like. It's just the intuition is that you're scanning a sequence of inputs. So taking a step back and returning to our problem of name matching, let's see what it looks like when we put this all together. So similar to the neural machine translation setup, we're going to have an encoder module, which in this case is an English name reader. And then that's going to compress our name into something that a Japanese name generator can transliterate. Because again, remember that modeling the dynamics of transliteration is the first step of doing name matching. And we're going to see how we can take this and use it to do the name matching in a moment. So zooming in, it looks like this. We take each character, string it along inside of our LSTM, and we end up with this vector representing the entire sequence. And so the benefit of this, if you look at it from a high level, these two components serve similar purposes to the two types of probabilities that we have in our HMM, except instead of being super static and saying, this is the probability of all instances of the letter O corresponding to all instances of Japanese characters, we instead have a network that's building up this flexible representation of all of the dynamics of the sequence as a whole. And so from this, it's much more straightforward to model those dynamics when producing our transliteration. And so this much more context-rich representation can capture all of these nuances of multi-character sequences or pronunciation affecting suffixes and so on. So once we have the ability to transliterate, all we're going to do name matching is run that transliteration step in reverse to get a score. So what does that look like? So this diagram is rather similar to the one that we looked at before, except you see that instead of the characters coming out of our decoder, they're now being fed in. And then this is building up some representation of our of the likelihood of seeing this sequence so far and ending up with a score at the end. Now, that might intuitively make some amount of sense, but it's interesting to talk about what this actually means from a technical standpoint. Running a generator in reverse. So to understand how this works, we need to think about what the decoder is actually doing. So the notion of a decoder just producing a character is a bit of an oversimplification, because it's not just a black box where a character comes out. Instead, what it will do is at each point in time, we will have an output that represents a probability distribution over all possible characters, in this case, Japanese. And typically what you would do is just say, okay, well, the most probable character is the one that is here. And so that's what we're going to use at this point in time for our decoding. So roughly speaking, this means that the prediction by our model is really just the, if you're familiar with the terminology, the maximum likelihood prediction of this probability model that we have in the top right here, where the encoder will condition this distribution on the English word, and then we pick the most probable Japanese word based on that out of all possible transliterations. And so the reason why it's interesting to make this this jump in interpretation is because once we can think about these outputs in this way, we can then see in a pretty straightforward way how we can start querying this distribution with a given transliteration and see what the probability of that is. So this is going to look like this, where instead of using the distribution to select the next input to the decoder, we're just going to feed in the known name that we're trying to score. But what we are going to do is we're going to take these probabilities that are outputted by the model, and we're going to see how well our given name aligns with what the model would expect the transliteration to be. So intuitively, what we want is some sort of measure of surprise of, how surprising of a transliteration is this Japanese name for the given English name. Like intuitively, we've been looking at the example Tupac for these last couple slides. So we would expect the proper transliteration of that to be not very surprising for the decoder, because that is pretty much in line with what we would expect it to produce. However, if we give it the transliteration for John or something like that, we should expect that to be rather surprising. So there's a measure to do this from information theory. It's known as perplexity. I'm not going to describe the details of what the intuition is behind the measurement or anything, but just take on faith. It measures this notion of surprise. And so because we want less surprising inputs to have a higher score, we take the reciprocal of it. And voila, we have a way of doing English-Japanese name matching in a totally data-driven way, without any sort of domain expertise or anything. And again, English and Japanese here is really just illustrating. I mean, this could be any pair of languages. So coming back up for air for a moment, this work that our team did was inspired by a customer who came to us with a list of names that our HMM was poorly matching. They was coming back and saying they were a match, when in reality they were not the same name. So we took that request, we built this model, and then we tested that list of names using it, and we found a 75% error reduction on that data set, which we thought was great. Of course, your mileage might vary depending on what your application is. But what we will say is that for our internal test data set, when we evaluated this model on that data set, we had a 10% accuracy boost, which might not sound substantial on its own, but there's two things to remember here. One is that the model is, the HMM is not bad in the first place. And so because of that, the scores improvements that we typically see when we make an update to the HMM are on the order of like a 1% or less increase in accuracy. So a 10% increase is incredibly substantial. However, there is no free lunch in this world, unfortunately. So anyone who is well acquainted with these neural technologies knows that there's one downside to all this, and that is speed. So when we compare our hidden Markov model to our neural network sequence-to-sequence architecture, you can see that there's a substantial slowdown. I mean, of course, we're expecting some amount of trade-off. I mean, we're using a more sophisticated algorithm, so it's not going to be as fast as the HMM. But like, just from the standpoint of, you know, having software that works for our customers, I mean, we want the speed to be ballpark similar, you know. I mean, a 25 times slowdown, which is about what this stabilizes to, is really not acceptable. We would like something that's at least roughly similar to the HMM. However, all hope is not lost on this front, as Carmel will now describe.
Hello, guys. So as Philip mentioned in the previous slide, and if you're looking at a more detailed version of our seek-to-seek architecture, there are three components: the encoder, the decoder, and the attention. Each is a separate neural net with its own purpose. So the encoder encodes the information of the English input name, and the decoder generates the corresponding katakana name. The attention determines which information is important in the encoded sequence on each character generation. Attention is often used in sequence-to-sequence problems, and it allows the decoder to dynamically attend important characters from the input and to automatically increase their weight when decoding. I'm not going to go into more details here, but this idea is explained in different resources online. So LSTM is a natural architecture for sequential tagging and sequence-to-sequence problems, since LSTM was designed to handle data that is encoded with temporal information like text. However, LSTMs are relatively slow due to the large amount of calculation that takes place during inference. The attention part makes things even worse. So the first step was to get rid of the attention model and let the decoder use only a static vector of information from the input text. That didn't change much, and we were still looking at a relatively slow process. Since in our case, both the encoder and the decoder are based on LSTM, we were looking for ways to reduce the number of calculations by considering different architectures, at least for our encoder. Then we decided to experiment with convolutional neural network, which is a different kind of neural network that people typically use for computer vision. For now, the decoder and the score function remained untouched. So what is a CNN? CNN is a neural network with weights, loss function, activation function, and so on. But its unique design enables recognizing patterns or features over space, or in other words, spatial features. Also, it's less about encoding temporal information and time series. CNN layers contain filters, and each filter is responsible for detecting a different pattern. As we go deeper into the network, the filters are recognizing more detailed structures. In computer vision, they could be objects like wheels, wings, eyes, and so on. The nice thing about CNN is that it may recognize features in different locations in the input without seeing them in that particular location during training. In other words, those features are location and rotation invariant. For example, in the following picture, the filters in the first layer may detect lines, and the filters in the next layer may detect structures like nose, ear, and mouth. And the last layer may detect the full object, the whole dog. So let's go back to our problem. How do we use CNN and NLP? So we can look for patterns in the text. As always, the first step is to turn our text into vectors. Typically, embedding is the way to go, but of course, we can vectorize the text in any way we want, like one-hot encoding, for example, as long as we have our text represented as a matrix. Now, the filters in the layers can look for patterns in the embedding matrix the same way as in pixel matrix of an image. The only difference is that every filter is in a different size, and instead of detecting pixels or structures, they are detecting consecutive token patterns. Sorry. For example, if a filter has a weight of 5, then it can see 5 consecutive tokens and search for them in the text. You can think of it as a combination of a lot of different n-grams. In the following example in the sentence, wait for the video and don't rent it, one filter will detect the combination wait for, and another filter may detect the combination wait for that, and so on. So there are a lot of architectures out there. Why did we choose CNN? Speed. CNNs are faster by design, and the computation in CNN can happen in parallel. Same filter applied to multiple locations of the embedding matrix at the same time. while RNNs need to be processed sequentially, since the subsequent steps depend on previous ones. So we know it's faster. Why wasn't it our first choice? Context. Because we process each character separately, we lose the valuable information that can be extracted from context. The order of the characters in the name is important. Take, for example, the combination of the characters C and H. The transliteration of these characters separately and together is not the same. So to solve this problem, we use positional encoding, which is basically a standard embedding layer where the input is not the character itself, but the position of the character within the token. We calculate positional embedding and structural embedding separately and then sum both matrices. But as wiser man said before me, there is no free lunch and we had to pay the cost. Now let's look at the results. We tried two different CNN architectures with various hyperparameters, and we did manage to reduce the speed significantly, but we had to pay the price in accuracy. In the following table, we have the architecture type, the improvement relative to the HMM, and the speed relative to the HMM. We can see that the accuracy results of the CNNs are good, but not as good as the LSTM. But as you can see, there are good news. The speed performance is much, much, much better. So that's it from me. I'm going to pass the mic to Fear. Thank you.
Thank you. Thanks, Carmel and Philip. Very interesting. And we want to wrap this up. And so I guess the main takeaway here was a bit technical. But we can say, based on our ongoing research activity, that name matching can still be improved, right? It's still an open problem, and we continue to try improving the different algorithms that we have, at least for some specific language pairs. So like always, improving accuracy with the state-of-the-art neural networks come with a cost, as you saw, and which typically we pay in speed performance. But luckily this time we were able to find a solution in the shape of different architectures like CNN that captures most of the information that we need. And it's much faster and can benefit from running on a GPU much better than RNN does. And our plans for next steps is to get this technology to other language pairs, as well as working on a fully end-to-end data-driven name matching algorithms. It's something that we're working on right now, which basically will replace the manual process of doing all these fine-tunings and configurations for the individual algorithms. And of course, we'll keep you posted on this, on our research progress here in our next research seminar, webinar, hopefully sometime soon. And I think that's it for the presentation, and we can move on to get some questions from you guys. So thank you so much for listening and for attending.
Thank you very much, guys, for this great presentation. And now is the time for the Q&A. And remember to submit your questions. You just have to click on the Q&A icon on the bottom part of your screen. And while we're waiting for the questions to come in, even though I did see a few coming in already, I do want to remind you that this presentation is being recorded and a link will be sent to you tomorrow. If you enjoyed it, please share it. Also, if you're unavailable to stay for the Q&A session, when you leave the webinar, you will be directed to a survey. Please take just 1 minute to let us know your thoughts. Your feedback is so important to us and allows us to continue to improve the webinars that we're putting together. And I will talk about it, but there are some very cool webinars coming in the next couple of days as well. So we do have a few questions. The first one is about explaining how two names in a language pair can be compared and a matching score calculated. How can this be used in search context? So if I search in language A and find matching names in other languages. I don't know which one of you wants to take that.
I can take that. So yeah, so we have different ways of calculating that matching score. Specifically in this session, that was based on a neural network. The way that we use that is that the algorithm, the phonetic algorithm or model, is integrated into the name matching product, right? And so while searching for a name in a large list and in Solr or Elasticsearch, for example, so the first step is to pull some candidates from that list based on very simple techniques for doing text search. And but then so in order to do that, when we index the names in Solr or Elasticsearch, we generate some alternatives for those names. And when we come to do the search itself, then the matching algorithm takes place that calculates all these scores. So while you're doing the search, we calculate all these scores in real time, and then we allow you to actually filter out those names that are below a certain threshold, and you can play with that. So basically, it works smoothly when we integrate that model into our RNI plugin, right, that sits in Solr and Elasticsearch, and it works in different languages.
And you're kind of answering also the next question, which is, do you think that the algorithms you described here will work for other pairs of languages? Have you tried that already?
Yes. So Carmel is doing research right now on Arabic, Latin scripts, and it works pretty well too. And soon we will be able to support those languages. Currently we support other languages, but specifically we're talking about this model, the neural model that improves the false positive rates dramatically, as you saw. So yeah, so the news is that it works for other languages, and hopefully we'll be working on other languages and we'll add more models.
Okay, great, thank you. And there's another one which is more about what's the main disadvantage in using CNN for NLP? Why not using it always?
So I can answer that too, but weigh in, guys, if you want to add anything. A language has this, it's actually a sequence. You can treat it as a sequence of words or characters, right? So basically a language has long dependencies or long distance dependencies between words. And that's very important. That context is very important, right? So when you try to do something or predict something about a specific word, sometimes you need information that comes from another word that is located very far from that particular word. And RNN, or recurrent neural networks, or all these flavors of RNNs, they take that into consideration. They encode all that information, the long distance dependencies, while convolutional neural network is more focused on local special features. But still, having said that, I believe that with all these long distance relationships between words, most of the information still exists locally, right? So a CNN can still capture most of the information that we need, and it runs much faster. So for some specific NLP tasks, it works very well, and we can benefit from the fact that it's much faster than an RNN.
Carmel, Philip, is there anything that you want to add to this answer?
Not me.
Okay.
No.
You gave the perfect answer, Kfir. So we'll move to the next one, which is about the training set we used to train the neural network. What was used there?
Carmel, do you want to take that?
Yeah, so the Japanese, we had 33,000 token pairs, English and Japanese. And we divided the test set and training set into 90% and 10%.
90% training data and 10%.
Yeah, sorry, of course, yeah.
So we had pairs of names annotated, right, created manually or curated by human.
Yeah, English and katakana.
Great, thank you. And so is this version of Rosette available for testing yet?
Yes, the Japanese version is available, but not the model, the last model that Carmen mentioned, the CNN model, the convolutional model is still in research mode. So we're sharing, some initial results with you guys, but the recurrent neural network that we described is in production.
Awesome. So I'm waiting for more questions to come in. That was the last one I had. So while the last questions come in, just wanted to let people know that we'll be hosting a webinar tomorrow called Smart Matching for Screening, which is a more of a high level overview of how smart name matching is deployed in critical business systems. So today you've learned about the algorithmic behind it, and today you learn about the use cases and how it's being deployed. And I don't see more questions coming in for the moment. And I don't see anyone typing. So maybe, unless you want to add anything, one of you wants to add something, information, what's coming down, what's in the roadmap or something like that. Do you want to give a little insight on what's coming in the next couple of months?
Sure. So our activities in name matching, as we said before, we're focusing on adding more languages and testing with more technologies. We always keep trying to improve our algorithms and make sure that they run as fast as possible. But besides that, we're also working on other technologies in the research team. We're working on event extraction, for example. That's a completely different task, but it's very, very interesting. And we are taking different approaches there. We already have a product and in beta mode that you can actually test. That means that we extract complete events from a text, including the trigger phrase or words, and then all the different roles, arguments for the event. So different relationships between words in entities. And we do that in different languages, and including English and Japanese. So that's one of our main focuses for now. And we're doing all other stuff, improving our existing algorithms for entity extraction for specific languages. We're working a lot on Korean, for example, right now, and some other stuff. Maybe I forgot something. You guys can add.
I know that this tool is pretty powerful, and we have a lot of people excited and eager to test it out. There's actually one question that came in while you were presenting the event extraction tool that we're working on. It's about the language coverage for our fuzzy name matching tool. Are you planning on Greek and Cyrillic to Latin matching?
It's a good question. Philip, yeah, I saw you wanted to answer.
Yeah, so, I can't speak to necessarily the specifics of what we're committed to support at this point. I guess maybe Fear would be the one to know about that. But what I will say is that what's really interesting about this approach that we're taking here is, there's a lot of opportunities for what's known as transfer learning, where, the idea basically being that you can imagine, if you remember, that you have like an English name reader feeding to a Japanese name generator, right? Well, typically, if you were to do, say, English Arabic, you would train a separate English name reader to an Arabic name generator. But the question is, why can you not just use the same English name reader for everything? And similarly, use the same Japanese name generator for everything coming into it. And so that's definitely an opportunity that we're looking to explore. If we can achieve that, then that certainly would dramatically improve the matrix of language pairs that we can support with our name matching technology. So, I mean, as far as the specific question of Cyrillic and Greek, I'll leave that to Jean and Kafir. Maybe they know. Or
so specifically plans for these languages, I don't have any such requests at the moment, but it's definitely something that we can come back to the person who asked the question, because we should consult with our product team so they get all the requests and everything, and maybe it's somewhere in the pipeline.
And that was our last question. I haven't seen any more pop up, but it's actually a great transition to the next slide, where you can find information about the different capabilities that we have and also the language that we support. You are more than welcome, and we encourage you to go to www.rosette.com. You have a list of all the different capabilities that we have, examples. You can actually test it there. So please go there. You'll find a lot of information. We post regular blogs as well. So this is a very good source of information. And as I said, to wrap it up, you can also find the list of all the different webinars that we're planning. As I said, tomorrow we have one about smart matching for screening. You can register there, see when they're happening. You can also go on, visit our LinkedIn page or Twitter. That's where we're announcing all the different events that are happening. And most of them, if not all of them, are online for the moment. That being said, thank you very much, to the three of you for this presentation, to you all for joining us today. I really hope you've learned something and you found this useful. Did I mention there's a survey at the end of this webinar? Again, please take 1 minute to fill it out. Stay safe and healthy, and we hope to see you again on the next one. Thank you very much, everyone.
Thank you.